So in this video, we're going to go over section 4.1 from our textbook, which talks about the first derivative of a function and how that's related to its graph. So first we'll look at increasing and decreasing functions. And in this video, we will be using what's called sign charts. We went over that in section 2.3, so it might be helpful to review that video or the lecture notes that go with it. But I will be using some theorems and bringing some of that stuff back for us to look at as we move through this video. But let's look at this example here. We have this function f of x, and we're given its graph. And we also have the sign chart for its derivative given here. And if you remember from section 2.3, in order to construct these sign charts, we have to break our number line into intervals. So we're breaking it into intervals based off of what's called partition numbers of our function. So partition numbers are numbers that make our function either 0 or undefined, and they essentially tell us, like I said, what intervals we're going to be looking at. So in this example, our partition numbers are -1 and 1, and so our interval is broken up into -infinity up to, but not including -1, and then -1 up to 1, and then 1 to infinity. So these are the intervals that we'll be looking at for our derivative here, and within each of these intervals, our sign of our derivative is not changing. And that's because of a theorem that we saw in section 2.3, which I'll bring back in a moment. But just a little reminder here of what it means for a function to be increasing or decreasing. And so essentially what this means is that we'll look at our graph here, and as we go from left to right, in each of these intervals, if our f of x values are getting bigger and bigger and bigger as we go from left to right, then what that means is that in that certain interval, all of our f of x values are getting bigger, so our function is increasing. And looking at the next interval here, as we move from left to right, we see that all of our f of x values are getting smaller within this interval. So here we'll say that our function is going to be decreasing. And similarly, in this interval here from 1 to infinity, we can see that our f of x values are getting bigger and bigger, so we can see that our function is increasing on this interval. Right? And then if we look at the sign chart that was constructed here, we see that where our f of x is increasing, our derivative is positive, and then where it's decreasing, our derivative is negative. So that brings us to this theorem here. So if we have some interval a to b, if our derivative is greater than 0, then our function is going to be increasing, and if our derivative is less than 0, so negative, then our function is going to be decreasing. And so that's given by this chart here. All right, so we'll use this theorem in the next several examples. Let's look at this one here. We want to find the intervals on which this function here is increasing or decreasing. So we're given this function, and this problem is broken into several parts. So first we want to find which values of x will correspond to our tangent lines, to our horizontal tangent lines. And we know that a horizontal tangent line just means our derivative is equal to 0. So we'll take the derivative of our function, of this guy. So we get 2x minus 6. And what we'll do is set this equal to 0 and solve for x. So we get 2x is equal to 6 by adding 6 on both sides, which tells us that x is equal to 3. All right, so for values of x equal to 3, we'll have a horizontal tangent line. All right, and then for part B, what we'll do is we want to figure out for which values of x is f of x increasing or decreasing. And just like we saw in the last example, what we'll do is construct a sign chart to determine when our derivatives are positive and negative. So when our derivative is positive and when it's negative, because we know by theorem 1 up here, that'll tell us when our function is increasing or decreasing. Now, I pasted this procedure in the notes just for a little reminder of the process for constructing sign charts. So this is from section 2.3, but in this case, we are looking at our derivative of f. So we're going to find the all partition numbers of f prime. Remember, our partition numbers will determine the open intervals on which our function, or in this case our f prime, is not going to change sign. So here, we're going to find the partition numbers of f prime of x. Because remember, we're using theorem 1 here, and we want to see when f prime is positive and negative. Okay, so the first thing we're going to do is find the partition numbers. So we'll label these as our steps. So we know that our derivative is this from part A. We know that when we set this equal to 0, we get that x is equal to 3. And since our derivative is a polynomial, it is continuous everywhere. So our only partition number in this case will be x is equal to 3. Alright, so we found all partition numbers for f prime of x. And now we're going to plot these numbers on a real number line to divide that guy, the number line, into intervals. Right, so we have our real number line like this. And we said that at this point, f prime of x is equal to 0. So our intervals are negative infinity up to our partition number 3, and then 3 up to infinity. Then the next thing we want to do is select a test number in each of these intervals and evaluate f prime of x, because remember we're looking at f prime of x to tell us if our function is increasing or decreasing. So each test number will tell us if f prime of x is positive or negative, and then once we have that information, we'll construct a sign chart, and then if we find that f prime of x is positive, then our function's increasing, and if it's negative, our function's decreasing. So this is going to be our test numbers, so we're evaluating our derivative at these numbers. So the first one I'm going to do is 0. 0 does live in this interval. And we can pick easy numbers like this. So we get negative 6, so we know that f prime at 0 is going to be negative. And then the next number I'll choose in the next interval is going to be 4. So we'll get 2, which is a positive number here. Alright, and then just to remind ourselves why this works, this is theorem 2 from section 2.3. So we see that if f is continuous on some interval and not equal to 0, then either this function is going to be greater than 0 or less than 0 for all x values within that interval. So essentially, if f is continuous and does not equal to 0 on this interval, then f of x cannot change sign. Because remember, if f of x were to equal 0, it would have to cross the x-axis here, and then we know that all of our f of x values are positive in this region and negative in this region. So if we cannot cross this x-axis, then we cannot change signs. So if we cannot change signs, then we can easily construct a sign chart using our test numbers here and these intervals here. So we're looking at the intervals, negative infinity up to 3. We have our partition number 3 here, and then 3 up to infinity. And so since we know that our function will, our derivative will not change sign in this interval, negative infinity to 3, we know that it's always going to be negative here. then we know that f prime of x when x is equal to 3 is just equal to 0. It's a partition number. And then we know that in the interval 3 to infinity, our derivative is always going to be positive and it's not going to change sign. All right, so then by theorem 1, whenever our derivative is positive, our function is increasing, and whenever it's negative, it's decreasing. So in my sign chart, I'm going to include that information. So in this region, it's decreasing, and in this one, it's increasing. All right, so we would write this as our function is decreasing on the interval negative infinity up to 3, and our function is increasing on the interval 3 to infinity. And then plotting some values here, we see that this is our graph, and we know that at the point x is equal to 3, we have a horizontal tangent line. So we'll draw that here. And so our partition number, remember, kind of splits this into two intervals. So negative infinity all the way up to 3, and then 3 all the way up to negative infinity. And so as we can see, our function is decreasing on this interval. As we move from left to right, all of our f of x values are getting smaller and smaller. And then after 3 and on, all of our f of x values are getting bigger and bigger, so our function is increasing, which matches what we have here. So here f of x is decreasing, and then here f of x is increasing. All right, so the next thing we're going to introduce are critical numbers. So if we have a real number x in the domain of our function, such that our derivative of our function is equal to 0 or does not exist, it's called a critical number of f. So this means when we say to find the critical numbers of f, what we do is we find the partition numbers of f prime of x. Now, something to note here, though, is just this little conceptual insight that the book provides. But critical numbers of f are going to belong to the domain of f and are partition numbers for our derivative. However, there are some partition numbers of f prime that do not belong in the domain of f, so in that case, they would not be considered partition numbers. All right. And then something else to note here, if f is a polynomial, then both the partition numbers for f prime and the critical numbers of f are going to be our solutions of f prime of x. All right, and then I just wrote this little blurb here. We can have a critical number of f, so that is a partition number of our derivative, such that our derivative is not defined at that point. And that's fine. We'll still proceed with as normal with this process, but we'll just note on the sign chart that f prime of x is not defined at that number. And then we're not going to go over an example like that in this video, but there is an example like this on page 243 of our textbook. Okay. So let's look at this example here. We want to find the critical numbers of f, the intervals on which f is increasing, where it's decreasing, and this is our given function f here. So remember, the critical numbers of f are going to be the partition numbers of f prime. So we want to find numbers that make our derivative equal to 0 or undefined. So the first thing we got to do is find the derivative here. We know the derivative of 1 is 0. The derivative of negative x cubed is going to be negative 3x squared. And this is a polynomial, so it's going to be continuous everywhere since it's a polynomial. All right. Now we want to see where f prime of x is equal to 0. And we know that this is going to be equal to 0 only if x is equal to 0. That's the only number we can plug in here to make this equal to 0. So our critical number is going to be 0, and our domain is divided into the intervals negative infinity up to 0 and 0 up to infinity. All right, so we know that we're then going to construct a sign chart. So we have our intervals negative infinity up to 0 and 0 up to infinity. And so what we want to do to construct our sign chart is to pick test numbers in each of these intervals. So I have some more room. I think I'll do that over here. Okay, so the first one I'm going to look at is negative 1. Negative 1 lives in this interval here. So plugging negative 1 into our derivative, we get a negative. Then we're going to plug in a number in this interval. So I'm just going to choose 1. Again, these can be easy numbers as long as they're in these intervals. And we see that we again get a negative number. So plugging this into our sign chart, we have a negative and a negative. So our function is decreasing on both of these intervals. And then we know that when x is equal to 0, our derivative is equal to 0. All right, so this tells us our function is going to be decreasing for all x values. All right. Then what we can do is plot a bunch of points, and we will end up with this graph here. And as you can see, our f of x values decreasing on this interval from negative infinity all the way up to 0. So all of these f of x values are getting smaller as we move from left to right. And then at this point here, our function is still decreasing as we move from left to right. All of these f of x values are getting smaller and smaller. And then we know at the point x is equal to 0, we're going to have a horizontal tangent line here. And we know that that's the, only tangent line we'll get at that point. If we were to try to draw any other tangent lines at that point, we'll intersect the graph in multiple places. And remember, our tangent line only intersects our curve at one point. Okay, so just something to note there. We do have a horizontal tangent line here. All right, let's look at a next example here. So again, we want to find the critical numbers of f and the intervals on which our function is increasing and decreasing for this given function here. So again, the first thing we're going to do is find the derivative of our function. And so there are several different ways we can do this. So we can rewrite this guy as this here. Oh, sorry, this should just be negative 1. As this here, and do our power rule, our power with our chain rule. So in this case, we would have negative 1 to the power negative 1 minus 1, so negative 2. So we get negative 1 on top, and then we have x minus 2 squared. All right. Another way that we can do this is we can do the quotient rule. Remember, low d high minus high d low, all over low low. So we can do that as well. You would get the same answer, but just rewriting this guy, so doing a little algebraic simplification, gives us the derivative in fewer steps. All right. So now what we want to do is figure out when this is going to be equal to 0 or undefined. Notice that this will actually never be equal to 0, because the only way that this can be equal to 0 is, or the only way that this fraction, or a fraction of this form, can be equal to 0 is if we have 0 on the top. And we just have -1 here, that'll never be 0. So now what we'll do is figure out when our function is going to be undefined. And we can easily see that this will be undefined if we are dividing by 0. So the only x value that will make this undefined is if we have x equals 2 here. Because then we get 2 minus 2, which would be 0 squared, and we can't divide by 0. So our domain is split into our intervals, negative infinity up to 2, and then 2 to infinity here. So we want to determine the sign of f prime of x in these intervals. So we're going to construct our sign chart. So we're going to pick test numbers in these two intervals and see what the sign of f prime of x is. So I'll pick 1, which is in this interval. So I'll get -1 over 1 minus 2 squared, just plugging it into our derivative. So we get -1 over -1 squared. So we'll get a negative here. So this tells me since f prime of x is negative, our function is going to be decreasing. Now picking another number in our interval 2 to infinity, I'll pick 3. Take -1 over 3 minus 2 squared. So we'll get -1 over 1 squared, and so we again get a negative number. So this tells us that our function is going to be decreasing for all values of x. And here on my right is a graph of this. We know that at the point x is equal to 2, right here, our function is undefined. Our derivative and our function is undefined. And if you remember from some previous sections, this actually means that we have a vertical asymptote at x is equal to 2. Okay, so our values are going to get super close to this, but not cross this asymptote. All right, and so as we can see, we move left to right, our function is constantly decreasing, and same on this side. As we move from left to right on this graph, our f of x values are getting smaller and smaller. And then something else to note about this problem here is if you look at our function f of x, we know that this guy will be undefined for any values that will make our denominator 0. And as you can see, the only value that will make our denominator 0 is 2. So this tells us that our domain of f of x is all real numbers except for 2. But we just said that x is equal to 2 makes our f prime of x undefined. So we would think that this would be a critical number. However, since 2 is not in the domain of f, it is not a critical number. All right, and so in this example, actually, our function has no critical numbers. All right, and that's fine. We would just state exactly that our function has no critical numbers, but we can still proceed as normal with this process of constructing our sign chart and determining that way the intervals for which f is increasing and decreasing. All right. So for the next example, we again want to find the critical numbers if there are any. of our function f and the intervals on which our function is increasing and decreasing. So we're given this function here. So again, we'll find our critical numbers. We'll first find the derivative of our function. And remember, the derivative of ln x is 1 over x, and then we just have our constant multiple out front. So we get 5 times 1 over x, and the derivative of x is 1. So just simplifying this guy a little bit, we have 5 over x minus 1. And so we want to combine these. We end up with 5 minus x over x. So this is our derivative, and we want to figure out when it will be undefined or equal to 0. So f prime of x is going to be equal to 0. What we're going to do is solve for x. So we'll multiply by x on both sides. So we get 5 minus x is equal to 0. So this tells us that x is equal to 5. Okay. So when x is equal to 5, our derivative is equal to 0. So that'll be one critical number. The next one you want to find when f prime of x is going to be discontinuous. And we know that that's going to happen when x is equal to 0, right? We can't divide by 0. We would have this here. So in this case, it looks like 0 is going to be a critical number. However, again, we have to look at the domain of our function. We have a natural log function, and this natural log is only defined for x values greater than 0. I'll write that here. So this means 0 is not in our domain. So x is equal to 5 is going to be our only critical number in this case. All right, so we just have to be careful with that, just making sure that we look at our domain and make sure that the partition numbers for f prime of x actually are in our domain of f of x. That's the only way they will be critical numbers of f of x. All right, so our domain is split into the intervals 0 to 5, and then 5 to infinity. So we're going to construct our sign chart and look at the sign of f prime of x for these intervals. All right, so we're going to pick a number in the interval 0 to 5. So I'm just going to pick 1, plugging this into our derivative. We'll get 4 over 1, which is positive. So we know that our function is going to be increasing. When picking a number in our next interval, 5 to infinity, we'll look at 6. And we know in this case we'll get -1. So this is negative here. All right, so that means our function is going to be decreasing in this region. And then we know that at x is equal to 5, our derivative is 0. All right. And then we actually have a sketch of this graph here. We see that at this point, we're going to have a horizontal tangent line. And then all of our f of x values before this point here are getting greater and greater as we move from left to right on this graph. So in this region, our function is increasing. And then after this point here, as we move from left to right, we see that all of our f of x values are getting smaller and smaller, so it's decreasing in this region. And that matches what we have here. All right, so the last two examples have given us a little bit of conceptual insight. The first being that we do not want to assume that all partition numbers for the derivative are going to be critical numbers to our function. Remember, to be a critical number of our function f, a partition number for f prime must also be in the domain of f. So we saw that in both of the last two examples. And we also want to make sure that the intervals on which a function f is increasing or decreasing always be expressed in terms of open intervals that are subsets of our domain of f. So for example, in the last example, we really should be writing the intervals out, saying f of x is increasing on, and give the interval, and decreasing on 5 to infinity. We want to express these as open intervals that are subsets of our domain because, like we saw in this last example, 0 is not included in our domain of our function, so it's not included on the interval which we're increasing. All right, so just keep this in mind here. And then the next thing we're going to look at is local extrema. So, when the graph of a continuous function changes from rising to falling, a high point, or what we call a local maximum, occurs. And then when the graph changes from falling to rising, a low point, or a local minimum, occurs. So looking at this figure here, we see that points C3 and C6 both point to high points, right? We have a higher point here and a higher point here. And then lower points occur at C2 and C4 down here. So as you can see, these guys are lower than all of the other points up here. So in general, we'll call f of c a local maximum if there exists an interval m to n containing that number c such that f of x is less than or equal to f of c. Okay, so essentially what this means is a local maximum occurs when we go from increasing to decreasing. And similarly, this value f of c is going to be called a local minimum if we have c within this interval such that f of x is actually greater than or equal to f of c for all values in this interval. And so this local minimum is going to occur when we go from decreasing to increasing. All right? And so whether it's a local minimum or a maximum, this value is going to be called a local extremum. And a point on a graph where a local extremum occurs is also called a turning point. I mean, this makes sense because these points happen when we're going from increasing to decreasing or decreasing to increasing. Right? So that makes sense that it would be a turning point. And then looking at this figure here, again, we see that C3 and C6 look like local maximums here. As you can see, our point is changing from increasing to decreasing to decreasing here. And then C2 and C4 correspond to local minimum. So you can see we're going from decreasing to increasing. And then here, decreasing to increasing. So later on in this chapter, we're also going to consider the problem of finding absolute extrema. So this is the y-coordinates of the absolute highest and lowest points on the graph. As we saw here with the local extrema, we can have multiple points. And it's really because we're looking at this point localized. So we're just looking at maybe just this region in general. And if we look at just this region, we can see that we have these two high points here. But if we were to zoom out and look at the graph as a whole, we would want to see the absolute maximum or minimum values, so the smallest or highest points of the whole graph. But we'll go over that in more detail later on in this chapter. All right, so let's look at this example here. So we want to use this graph of our function g to find the intervals on which our function is increasing, decreasing, and any local extrema. So right off the bat, we can see from infinity all the way up to this point -3 here, our function is decreasing. Then from -3 to 1 here, we see that our function is increasing. All of these f of x values are getting bigger and bigger as we go from left to right. And then from 1 all the way down to -infinity here, we see that all of our f of x values are getting smaller and smaller. So, like we said, our function is going to be increasing from -3 to 1. I'm sorry, I keep saying f of x, but for this example, we're looking at g of x. But we're increasing from -3 to 1. And we set our functions decreasing from -infinity up to -3, and then from 1 to infinity. Now, when we go from decreasing to increasing, we know that we're going to have a local minimum. So we can see that that occurs here when x is equal to 3. So we have a local minimum when x is equal to 3. So plugging this into our function here, at -3, our g of x value looks to be about -3. All right. We know that a local maximum value will also occur when we go from increasing to decreasing. And that happens at this point here, where x is equal to 1. And looking at our graph here, that occurs, we have x is equal to 1, so our g of x value is going to be 5 here. All right, so this is the actual point of our local minimum. It'll be -3, -3. And the actual point of our local maximum is 1, 5. All right. So let's look at this theorem 2 here. We're told that if f of c is a local extremum for our function f, then c is going to be a critical number of f. So we're going to use this to find the local minimum and maximum values when given a function instead of a graph. And so this theorem pretty much says that a local extremum can occur only at a critical number, but it doesn't imply that every critical number produces a local extremum. Okay, so in this figure above here, points C1 and C5 here, as you can see, are critical numbers, but our function does not have a local minimum or maximum at either of these numbers. And we can see that just because our function is decreasing here and it's decreasing there. And then for C5, it's increasing here and it continues to increase here. Okay. And so our strategy for finding this local extrema is going to be to find all critical numbers of f and test each one to see if it produces a local maximum, minimum, or neither. So we could have the case where we have neither. So this brings us to the first derivative test here. So if we let c be a critical number of f, we're going to construct a sign chart for f prime of x close to and on either side of our critical number c. So we have a few cases here. If we have the case where our derivative goes from negative to positive, and this change occurs at our point c, at our critical number, or what this means is our function is going to go from decreasing to increasing at this point, then this tells us that f of c is going to be a local minimum. So our function is going to go from decreasing, and then at this point c here is increasing. Okay, so this is when a local minimum would occur. Similarly, if our function went from increasing to decreasing at this point c, So it would look like increasing up to point C here, and then decreasing afterwards. We would have a local maximum. Lastly, if we have that our function is going from increasing and then continues to increase after this point C, we're not going to have local extremum. So we're not going to have a local maximum or a minimum. An example of this is if we have a function that's increasing, and then here's C, and then it continues to increase. Okay. And similarly, if we have a function that is decreasing and continues to decrease after this point C, we don't have any local extremum, and so we don't have a maximum or minimum. And an example of this would be if we're decreasing to C, and then we continue to decrease. All right, let me draw that a little nicer. All right. So here are some examples from our textbook here. And you guys can read through these, but they just give different examples of curves when we see that a function goes from decreasing to increasing or increasing to decreasing and so on. All right, so let's look at this example here. We're given this function and we want to find the critical numbers of f and the local maximum, local minimum of f, and then sketch the graph of f. So first, to find the critical numbers of f, we know that we're going to find the derivative and figure out what numbers will make the derivative equal to 0 or undefined. So the derivative of f of x is going to be 3x squared minus 18x plus 24. Okay, so just using our power rules here. And we know that this is a polynomial. So the domain is going to be all real numbers, so nothing's going to make this undefined. Okay, but we do want to see what values of x will make this equal to 0. So we're just going to solve for 0 here. We can pull out a 3 from every term here. Right, if we divide both sides by 3, we're not really changing anything. We just have 0 divided by 3 on the other side, which is 0. And so we're left with this, and we can factor. Right, we want two numbers that will multiply to be positive 8 and add to be negative 6. So that looks like negative 4 and negative 2. All right, so this tells us alrighty. So our domain is split into the following intervals. We have negative infinity up to 2, 2 to 4, and then 4 to infinity. All right, so we're going to determine the sign of our derivative in these intervals. So we'll construct our sign chart here. All right, so we'll pick some test numbers. We'll do that down here. I'm going to pick 1 in this interval here. So we'll plug that into our derivative. All right, so we'll get 3 minus 18 plus 24. So this will be positive. We don't need the actual number, we just need the sign. So this tells us that our function's increasing. Then we'll look at a number in this interval, 2 to 4, so we'll pick 3. And again, plug it into our derivative. So we'll get 27 minus 54, and then add 24 to that. So we end up with 51 minus 54, and that's negative. All right, so this tells us our function's decreasing. And we know that when f prime of x is equal to 2, that it's equal to 0. Sorry, we know that f prime of x is equal to 0 when we plug in 2. And since our function goes from increasing to decreasing, this means that a local maximum occurs at this point, right? Our function is going from increasing to decreasing. All right, now let's look at a number in this interval. So we'll plug in 5 into our derivative. And so we get 75 minus 90 plus 24. And so this will actually be positive. We have minus 15 plus 24. Right? So f of x is going to be increasing over this interval. And we know that f prime of x is going to be equal to 0 when x is equal to 4. And since we're going from decreasing to increasing, so we're going from decreasing to increasing, we're going to have a local minimum at that point. All right. Now what we want to do is actually find the f of x values for these local extrema. So our local minimum occurs when x is equal to 4. And so we want to figure out what that is equal to. So just so we have more room, plugging this into our function. We'll end up with 64 here minus 144 plus 96 minus 10. Right? And then this will end up being 6 here. All right, so our local minimum occurs at 4, 6. And then our local maximum occurs when x is equal to 2, so we'll plug that into our function. So then we get 8 minus 36 plus 48 minus 10. And so this will end up being positive 10. So our local max occurs at 2, 10. All right, so we've done parts A and B of this example, and now we want to sketch a graph of f. So I've already plugged in some points for this, and we do know we have a local max and a local min here. And so what we can do is use that information along with these points here to plot our graph. So we know when x is equal to 2, we have a maximum at 10, and then we have a minimum when x is equal to 4 at 6 here. Okay. We also know that f of x is equal to 6 when x is equal to 1. So something like this. When x is equal to 3, we have 8. And when x is equal to 5, we have 10 here. All right. Using that information, along with the fact that f of x is going to be increasing from negative infinity to 2. So we'll draw our curve like this. We're increasing from negative infinity up to 2. So all of our f of x values are getting bigger and bigger as we move from left to right. Then we know from 2 to 4 our function is going to be decreasing. So it's going to look something like this. And then from 4 to infinity our function's increasing. So it looks like this, all the way to infinity. And then we know that we have our local max and min here, and we also know that at these points, we have a horizontal tangent line, and our derivative is equal to 0. All right, so that was a rough sketch for that one. So the last thing we're going to look at, first this theorem 3 here, which just tells us if we have a polynomial like this with degree n, which is greater than or equal to 1, then this function is going to have at most n x-intercepts and at most n minus 1 local extrema. So just be careful with this. This is saying we'll have at most n minus 1 local extrema and at most n x-intercepts. But this is just a kind of way you can check your work. For example, in the last problem, we had a function which had degree 3. So this means we would have at most 3 minus 1, so 2 local extrema. And so if we did find 3 in this case, then we know we'd be in trouble. So this is just a little theorem that you can check your work with. But lastly, let's go into this example here. So this graph here approximates the rate of change of the US share of the total world production of motor vehicles over a 20-year period. And S of t is going to be the US share as a percentage, and t is the time in years. So we want to write a brief description of our graph, y is equal to S of t, and include any local extrema just based off of this graph here, which is a graph of S prime of t. But notice, this graph here essentially contains the same information as a sign chart. As we can see in this region here, from x is equal to 0 to 6, label that, S prime of t is negative. Okay. We can also see that S prime of t is negative on this interval here, from 16 to 20. And then S prime of t is positive in this region. So this is from 6 to 16. All right, so just based off of that information, this tells us that the US share, so remember the US share is going to be S of t, is decreasing the first 6 years, because we know that S prime of t is negative from 0 to 6, so for the first 6 years. And it will decrease to a local minimum, because we know that it then will increase for the next 10 years, from year 6 to year 16. And that'll increase to a local max, because we know that it will then decrease for the last 4 years, from years 16 to 20. All right, and then we want to sketch a possible graph of S of t. I've done that here. So this is just a super rough sketch because we don't really know much about this given, I guess, the lack of info because of S of t, or the lack of info about S of t. So we don't actually know what the y-axis, the scale for the y-axis, but this is just a rough sketch indicating our local min and our local max here, and then the fact that our f of x is going to be decreasing up to this point, increasing to this point, and then decreasing again. Alright, so that'll be it for this video.